Welcome all to Anudeep YourStudyBuddy. We have started with the topic matrices, and today we are going to discuss about how to find the inverse of a matrix using the elementary row transformation. So we'll be discussing both the methods, row transformation as well as the column transformation. Let us understand what is the meaning of transformation and how to perform row and column transformation to get the inverse of a matrix. So let us proceed.
Elementary transformation. Let us understand what is the meaning of elementary transformation in a matrix. So it can be achieved in three different ways. First, by interchanging any of two rows, any of two columns. That is, if we interchange the ith row with the jth row of a matrix, after interchange, the original matrix is transformed into a new matrix. For example, Ri is exchanged with Rj. That is what we are interchanging every element of the ith row with every element in the jth row. So that is what is a row operation that we call. By interchanging these two rows, we form the transformation in the matrix. Similarly, you can have the transformation by swapping the two columns. Column number Ci, that is ith column, is interchanged with the jth column. So that can be achieved. This is called the elementary row or column transformation just by swapping the two rows or columns. Let us understand by using example now. You can see a matrix A on the screen with the elements 1, 2, 3, 4, and you can see that it is a square matrix with two rows and two columns. So if I swap the elements in R1 to R2, so what will happen? Whatever we are having in R2 will be shifted to the R1 as the first row, and elements in 1 will be shifted to the second row. That is why R2 contains the element 3 and 4. It will move to the first row. That is, first row will be now 3, 4, and the second row will be 1, 2. Similarly, if we interchange the column C1 and C2, so you can see that first column was 1, 3. Now it has interchanged with 2, 4. So the formation after the transformation will be 2, 4, 1, 3. Now the second method of transformation is by the multiplication of the element of any row or a column by a non-zero scalar. It should be a non-zero scalar because if you multiply by the 0, the matrix element will lose its property, element will turn to 0. So here if you assume k as a non-zero scalar and it is multiplied to the specific row Ri, then you have to multiply each element in that row by k. For example, as you can see on the screen, A is a matrix with the element 0, 2, 3, 4. Then if I assume or I follow the row operation as R2 changes to 4 times R2, so R2, that is the second row element, should be multiplied by the non-zero scalar 4. So as you can see, first row is intact, 0, 2, it is as it is. But then the second row 3 is multiplied with 4 because k is 4 here. So 3 4s are 12 and 4 4s are 16. That is how the operation works. Similarly, same thing can be achieved by performing operation on the columns. You can multiply the column elements by the scalar. Again, we are exchanging C1, that is the first column is multiplied with negative 3 into C1. So the second column remains as it is, 2, 4 is intact, but there are changes in the C1, that is 0 into minus 3, that is 0, and 3 into minus 3, that is minus 9. They are very easy to perform operation, but it should be clear in your mind because this will be used to find the inverse of the matrix. Now the third way to perform transformation in the matrices is adding the scalar multiples of all the elements of any row or a column to the corresponding element of any other row and column. So what we are doing, we are not just simplifying by a scalar to a particular row, but at the same time we are adding those elements to a specific or a different row to get all together the different element performing that task. As you can see on the screen here, k is 2 and we are performing the operation R1 changes to R1 plus 2 times R2. So here, what is the element in R1 position? In the first matrix A, that is minus 1, 4, 2, 5. In the row 1, we have minus 1 and 4. So first thing is R1 plus 2 times R2 we have to perform. So R1 elements will remain as it is. Minus 1 is as it is plus 2 times the element in the R2 position. It is 2 times into 2. Similarly, In the first row, we have the number 4 plus 2 times the element in the second row, that is R2 is 5. It is 4 plus 2 into 5. So ultimately, what you get as answer is only the elements in the first row is going to change. R2 remains same, 2 and 5 remains the same, and the elements after the row operation in the R1 will change to 3 and 14. Now let us understand what is the inverse of a matrix. A is a square matrix order M. So now we are talking about the square matrix. So just by specifying either the row number or a column number, you can identify how many rows and columns it has. So if when I say M, there are M number of rows and M number of columns. So A is a square matrix of order M, and if there exists another square matrix B of the same order, that is B is also the same order as M, such that A into B is equal to B into A, that is equal to I, where I is the identity matrix of order M, and B is called as the inverse of A and is denoted by A inverse. So what is the meaning? We discussed about the compatibility of the matrices in the previous lecture. We discussed that when we are talking about the square matrix of the same dimension, they are always compatible. And this is what we are making use of the concept here. B is same as order as A. So they are compatible. So we can perform the multiplication operation. And when we are multiplying these two, we are going to get the answer as identity matrix. That is, the elements in the identity matrix is 1, 0, 0, 1. If it is a dimension 3 by 3, 1, 0, 0, 0, 1, 0, 0, 0, 1. So, what is the necessary condition for the inverse matrix to exist? The necessary condition is determinant of A, it should not be equal to 0. That is, A should be a non-singular matrix. Inverse of a non-singular matrix by elementary transformation. If inverse of A exists, then A into A inverse equal to A inverse into A equals to I. We consider the equation or a rule A into A inverse equals to I when we are finding out the inverse of matrix using row transformation. Following are the steps that we are going to make use of when we are reducing the 3 by 3 singular non-singular matrix while finding out the inverse. So first of all, reduce the element at the position A11 to 1, reduce A21 and A31 to 0, then reduce A22 to element 1, reduce A12 and A32 to 0, reduce A33 to 1, then reduce A13 and A23 equal to 0. Remember that similar working or tools may be used if you are using the column transformation.
We have been given the matrix A and we want to find inverse of A using the elementary row transformation. We have just now discussed how to perform the row transformation with the given matrix. Let us apply those concepts to find the inverse of this given matrix. As we all aware about, before we start finding out the inverse, it is mandatory to check if the determinant of A is not equal to 0. Find out the determinant of A and that comes out to be equal to 1 and which is not equal to 0. That implies A is non-singular. So that now we are confirmed that we can find the inverse of the matrix A. Finding out the inverse of A using the row transformation, we can use the formula A into A inverse is equal to I. Let us substitute the values. We know the value of A. So that is equal to 3, 2, 6, 1, 1, 2, 2, 2, 5. The inverse we have to evaluate. And I is the identity matrix of the order 3 by 3 is 1, 0, 0, 0, 1, 0, 0, 0, 1. Now what I observe, if I want to get the element at the position A11 equal to 1, I can just swap the R1 and R2. So if I interchange the rows R1 and R2, I'll be getting the A11 as reduced to 1. So let's perform that operation first. So it will be 1, 1, 2, 3, 2, 6, 2, 2, 5. Similarly, same operation we have to perform on the right hand side. So we are going to swap these two rows. So row 3 becomes intact, remains intact. 0, 1, 0, 1, 0, 0. Now, to reduce the element at the position A21 and A31 equal to 0, we can write the row operation for R2. What I can write? R2 changes to R2 minus 3 times R1. And for R3, I can write R3 minus 2 times R1. So after performing this operation, now as you can see, R2 and R3 they are changing, R1 is same. So let me rewrite the elements in R1 position first as it is. And now let us perform the row operation R2 minus 3R. So R2 is 3, 3 minus 3 times R1, that is 3 minus 3 is 0. 2 minus 3 will give me minus 1. 6 minus 6 will give me 0. Now R3 minus 3 minus 2 times R1. So 2 minus 2 will be 0. 2 minus 2, again it will be 0. And 5 minus 4 will give me 1. Same operation we have to perform on the right hand side. So here it will be R2 minus 3 times, it will be 0. So 1 as it is. Then you are getting 0 minus 3 and it will be 0. Now for R3, it is first element is 0 minus 2 times R1. So 0, it is 0 minus 2. And lastly, 1 minus 2 times R1, that is 1. So now we have at A11 we have 1, 0, 0. At the position A22 we need plus 1. So let us multiply R2 by minus 1. So throughout the row R2 we have to just multiply by minus 1. So what will be getting? 1, row 1 and row 3 will be as it is. Again here also 0, 1, 0, 0 minus 2, 1. Simply multiply by minus 1. Here will be minus 1, 0. So this is now to reduce this element A12 equal to 0, we can perform the operation R1 changes to R1 minus R2. Again, we are just performing changing the R1, R2 and R3 will be as it is. So let us rewrite them again. So it will be 0, 1, 0, 0, 0, 1, minus 1, 3, 0, 0, minus 2, 1. Now, let us simply subtract R1 minus R2, 1 minus 0 is 1, minus 1 minus 1 is 0, 2 minus 0 is 2. Again, 0 minus of minus 1 is plus 1, 1 minus 3 is minus 2, and 0 minus 0 is 0. Now we have to reduce this A13 equal to 0, so we can perform the operation R1 changes to R1 minus 2 times R3. So we are simply changing R1 again, so let me rewrite R2 and R3 as is. So what we get 0, 1, 0, 0, 0, 1, minus 1, 3, 0, 0, minus 2, 1. So R1 minus 2 times R3. So 1 minus 0 that is 1, 0 minus 0 is 0, 2 minus 2 giving you 0. It is 1 minus 2 times R3 that is 0, that is 1, minus 2. Minus 2 times R3, so it is plus 4, minus 2 plus 4 that is plus 2, and 0 minus 2 that is minus 2. Now as we can observe on the left hand side, this is nothing but the identity matrix A into A inverse is equal to 1, 2, minus 2, minus 1, 3, 0, 0, minus 2, 1. So I into any matrix is matrix itself. So what we can write? A inverse will be, it is the same matrix. So this is what is the answer for your A inverse. Now let us solve the same problem using the column transformation. So it's the same matrix A that we are going to use and we are going to find out the inverse, but now by the method of column transformation. So the first step will be the same. We need to identify whether the determinant of A is not equal to 0, that is A is non-zero. This is what we have already verified. So now let us proceed with the column transformation. With the elementary column transformation, we use the formula A inverse into A equals to I. So let us substitute the values. We have to find A inverse. Value of A matrix is given to us 3, 2, 6, 1, 1, 2, 2, 2, 5. And I, again the empty matrix 1, 0, 0, 0, 1, 0, 0, 0. So now with the column transformation, if I can perform C1 changes to C1 minus C2. So I'm changing only column 1, column 2 and column 3, they will be as it is. So I'm just rewriting them. 2, 1, 2, 6, 2, 5 equals to again 0, 1, 0, 0, 0, 1. So now the option is C1 minus C2. So 3 minus 2 is 1, 1 minus 1 is 0, 2 minus 2 is 0. Similarly, 1 minus 0 is 1, 0 minus 1 is minus 1, 0 minus 0 is 0. Now to reduce the element A12 equals to 0, we can perform the operation C2 changes to C2 minus 2 times C1. So again, C1 and C3 remains constant. So let us rewrite them. 1, 0, 0, 6, 2, 5 equal into A inverse equal to, here again, C1 that is 1 minus 1, 0 as it is, and 0, 0, 1. Now let us perform the operation. Now to reduce the into minus 2 times C1, that is 2 minus 2 is 0. We have zeros here, so it is simply 1 minus 0, 2 minus 0 as it is. Here we'll be getting 0 minus 2 times C1, that is 2 times 1, that is minus 2. Here it is C2, that is 1, minus of minus 1, that is 2. So 1 plus 2 is 3. Here it will be 0 and 0 will be 0, 0. So now let us reduce the element A13 equals to 0, that is operation will be C3 minus 6 times C1. So first two columns will be as it is, and when we perform this after performing the operation C3 minus 6 times C1, that is 2 minus 6 times C1, that is 2 will be as it is. Again 5 minus 0 will be simply 5 as it is. Here what will be getting? We'll be getting it is 0 minus 6 times 1, that is minus 6. Here it is 0 minus 2 minus plus 6, and it is simply 1. Performing the now to reduce the element at the position 8 to 3, that is 2 to 0, we can perform the column operation as C3 changes to C3 minus 2 times C2, and when you perform this column operation, this is what we'll be getting. Next step will be, as you can observe, only element in the column 2 has to be reduced to 0. So now let us write the operation as, we can write this operation as C2 changes to C2 minus 2 times C3. Right? So this is what we'll be getting the answer when we reduced the given matrix by the elementary column transformation. And now as you can identify, this is nothing but the identity matrix. So A inverse into I will be the matrix that we have obtained just now. And because it is multiplied by a unit matrix I, this is what is the answer, final answer for the A inverse for the given. So like we discussed, the problem on matrices finding the inverse using the elementary row and column transformation today. This matrices topic is pretty easy and you often get the 4 marks question in your board exam. So practice them well and stay tuned for the upcoming videos. We will see you very soon. Thank you.